Number 34, determine if point, let's see, critical number, and determine whether that's a minimum or maximum. All right, now I chose a different approach on this one, which I'll explain. And I'll tell you what you could have done without actually doing it here. But so I took the derivative, pretty easy function. So it's telling us that 2 is, decide if it's a critical number, which it is. So if you take the derivative, it's 6x squared minus 6x minus 12, factor out the x minus 2, x plus 1, so 2 and negative 1. So that rules out C as the answer. So it is a critical number. Now you could have done a sign chart at this point. You could have drawn a sign chart, did the intervals. Really, you only have to check at 2, whether before 2 and after 2 to see if it's going plus minus or minus to plus. But as I mentioned right here, that's what this is saying. You could use a first derivative sign chart. But it's just quicker and easier to go with that second derivative sign chart. So I just took the second derivative of this function, which is 12x minus 6, and plugged 2 in there, which gives you 18, and that's similar to the problem up here. This one of them I did with the second derivative sign chart there, or a second derivative rule for critical numbers. But you take the second derivative at 2, you get 18. If it's positive, you have a min. There we go, from back up here at number 30. And it's positive, it's a min, negative, it's a max. So 18 is positive. So we have a minimum at 2. And then the negative 2, that's not an interval. That's the point 2, negative 2. So that negative 2 comes from plugging 2 back in the original function. But clearly, you don't consider the other answer D. It says maximum. Yeah, they kind of gave you the Y value there. But just in case, had it said 2 different minimums where the X equals 2 and 2 different Y values, then you would have had to plug it into the original to figure out which one was right. All right. Now, number 35, looking for inflection points. So that comes from the second derivative. So we take the second derivative, set it equal to 0. Pretty easy for this polynomial, so I won't worry about going through the derivative steps there. I'll assume you can do that. But anyway, we take the function here, second derivative, set it equal to 0. Factor out a 12, makes it easier. Get rid of the 12. Oh, that's a typo. Let's see. It's supposed to say x squared minus 5x plus 4. Let's see. All right. That'll do. That factors into x minus 4 and x minus 1. So that gives me 4 and 1. And so I make a second derivative sign chart. Put 1, put 4 in there. Pick your test values. I use 0, 2, and 5. I guess I didn't show on a calculator or anything. But, you can look in my notes and see how it's done. But anyway, I would have put, those numbers into this second derivative over here right there, or the factored form also. And I get plus minus plus. So concavity goes up, down, up. So an inflection point occurs anywhere that's not a discontinuity, but where the second derivative equals 0 or is undefined, so like the critical numbers. And you must change concavity at that point. So up to down or down to up, both constitute inflection points. So we have 1 and 4 will be the 2x values that represent the inflection points. Number 36, concavity, is asking for concave up. Obviously, it could have asked for both concave up and concave down, which I have answered down here in my chart. Take the second derivative of this polynomial, which is pretty easy. So you get 24x minus 90. Set that equal to 0. You get 15 over 4, so that's the value that separates my two intervals. Put your two test values in. You put in 0 in the second derivative, 24x minus 90, you get negative. Put 10 in there, you get positive. So we definitely have an inflection point there, even though it's not asking for it, but there is one there. But since it's only asking for concave upward, and it looks like I made a mistake on circling the correct answer here. I answered it concave downward, so it should be answer D. Concave downward would be answer B. So 15 fourth comma infinity would be your concave up interval. And like I said, that was a point of inflection. Use the graph to locate the local extrema. Identify the intervals where function is concave up or concave down. And let's see, inflection points aren't that easy to see. Like you see, I labeled maxes and mins are easy to see, being top of the hills, bottom of valleys. But the inflection, you see this first interval here is concave down, and then it changes to concave up. But it had to change somewhere in there, right? It had to make some sort of transition. So I just kind of put right where it would be. And you see they're not trying to really trick you up here. They're kind of indicating that it's definitely 0. In other words, they don't have answers like 0 or 0.2 or something weird like that. So this is pretty easy. So you've got the local min at +1, max at -1, and then the concave up. Dang, nope. I'm wrong again here. Hope the answer key on the original file is correct, and even though I'm wrong here, it's concave down on 0 to infinity, and then concave. Oh no, I was right. See, now I'm worried about being wrong here. I was right. I misread this. It is. I thought I assumed they were writing it from left to right on the intervals, but they weren't. So it is concave up on 0 to infinity, and then concave down from -infinity to 0. All right. '38. Properties and limits to decide whether or not the limit exists. And you can go back and look at my notes on how to handle the infinity limits. It's pretty much the same principle. That's from 3.5, the way you determine horizontal asymptotes. Also, same kind of idea here. Well, anyway, you look at now. Keep in mind the powers may not be in perfect order here, so you have to search the numerator and the denominator. But you see x squared is the largest power on top. Y squared is the largest power on bottom. X squared on top, x squared on bottom. And so when they have the same powers, you take the ratio of their coefficients, so it would be -3 over 4. And so it would be -3/4. In other words, you guys kind of wrote that, because anytime you're doing an infinity limit, you really can ignore all the other smaller powers. Obviously, algebraically, you can't do that. But when it's an infinity limit, you can do that. So therefore, it'd be -3 over 4. Now this next one, 39, is a little tricky. Once again, algebraically, it'd be wrong to split those up into separate pieces, but because it's an infinity limit, we can. So the determined power, though, we have to take the square root into play here. So you take the square root of 5x squared. You don't care about the 4. So that would be the square root of 5 times x. Now you have matching powers. So therefore, the powers are the same. So you would just take the ratio of the coefficients. And it's square root of 5 over 5. So that would be the result for that one. So it's kind of tricky with that square root. Okay, number 40. X is going to limit of x going to negative infinity of cosine of 5x over x. This one's I officially solved it using the squeeze theorem, but you can almost kind of use logic on this too. I just placed the fact that the squeeze theorem says if you know that the function, the ratio is between two other functions, you can clearly say that's true, and if those outside limits have the same result, that means the one that's squeezed between them would have to go to the same result. So that's what I did here. Since cosine of 5x over x would always be between negative 1 over x and 1 over x, because cosine of 5x would always be between negative 1 and 1, since both those, then the outer limits would both go to 0, therefore the middle limit, which is the one we're trying to solve, that would go to 0 also. Another way to think of it is, as that denominator, even though it's growing, massively negative, the numerator would be just a number, somewhere between negative 1 and 1 at all times. It's not really growing. It's not really, so it's a constant. Therefore, a constant over infinity, either infinity, positive or negative, would go to 0. Now the next one, look here, the largest power on top is 6x cubed. Largest power on bottom, the x cubed, and then x squared, but you have to keep the negative here, so it's negative 6x squared. Very important to keep that negative in front of it, because that does affect the answer. So when you have this case, now when you have larger power on bottom than top, it goes to 0. And then we've already handled a couple of problems ago the case where it's the same, same exponent. But this case, you have to then reduce the x's and see what's left. And of course, I canceled the 6's, and that reduces to negative x. Then you put your infinity, whether it's positive or negative, you put that in there for what you have left, and then determine which infinity the answer is going to be. It's going to be one of the infinities. So in this case, that's why that negative is important right down here. Because put the negative in there, negative of negative infinity actually makes the answer positive infinity. So that's the way you kind of algebraically work it out. Of course, you could then also take a massively large negative number if you wanted to in the calculator and put that in there and see what it's approaching. But that's the way to do it algebraically, is the way I did it here. Okay, let's see. Asymptotes. Okay, horizontal asymptotes, basically the limit as x goes to infinity, either both infinities, fine, but positive infinity is good. So this one you can see 2x over x, has the same power, so it's just 2 over 1. So the limit, since the limit as it goes to infinity equals 2, that means the horizontal asymptote is y equals 2. And then vertical asymptote is basically, you don't have to go through the formality of doing the one-sided limits. Technically it's from the one-sided limits going to infinity. As you approach the value from the left and right, they would either go, it can go to opposite infinities, and it's still an asymptote. But probably the easiest way to handle this one would be, okay, if there is one, there's only one choice it can be. Look at the discontinuities that make the denominator equal to 0, when this case is negative 3. So the key is, if it makes the denominator 0, but does not make the numerator 0, then it is a value that's a vertical asymptote. So in other words, if you had an x plus 3 factor on top and an x plus 3 factor on bottom, negative 3 would still be a discontinuity, but it would not be an asymptote. Actually, it would be a hole kind of in the graph, not an asymptote, because the limit would exist. But in this case, it's the -3, because -3 does not make the top part equal 0. So you have y equals 2, and then x equals -3. So those would be your two asymptotes for that problem. 43, looks like we're doing a lot of stuff to this one. This is a good one. I like this because it has that fractional exponent in there you need to pay attention to, because that's that weird definition of critical numbers. In fact, I'll go ahead and come over here and then take care of all this, and then we'll worry about what all the questions asking for. It talks about concavity and increasing, decreasing, so we know we need the first and second derivative information. So take the derivative. Don't forget the chain rule. So 2/3, bring the power down, subtract 1, -1/3. And the derivative of the inside is 4, so you get 8/3, and then 4x minus 5 to the 1/3 on the bottom. Now, if you set that derivative equal to 0, you're not going to get anything, because the numerator is 8, so you won't get a critical number that way. But you do get one by that other rule of critical numbers that I have right here. If f prime is undefined while that f is defined at any particular value, you have a critical number. So see, 5/4 makes that derivative undefined, but it would not make the original function undefined. So we do have a critical number 5/4, which I have as 1.25 right down here. That same kind of rule applies to the second derivative. Take the next derivative, -1/3, bring that down, times 8/3. I think I made a mistake here. Oh, no, I didn't, because, okay, it would be -8/3 times -1/3 is -8/9, but when you take the derivative of the inside, that gets a 4, so that's what makes it -32/9. And then you have 4x minus 5 to the -4/3. So that same 1.25 will also go on the second derivative chart. Separates it. Now, so you see, once we identify those values, we do the same business. Put in your test value, you get negative to positive. So you can see the function is going to decrease before 1.25, increase afterwards. And then for the next function, the second derivative, you get negative and negative with both intervals. So the concavity goes down and then down again. So we have no point of inflection, because remember, it has to change concavity. So we have decrease, increase, and we will yield a relative minimum there when you go down to up. That's a minimum. No inflection points. So let's look at answer D here. So that's, it's got the increase over here, right there. The decrease, negative infinity to 1.25 right there. Relative min at 1.25, 0. That means when you put the 1.25 back into the original function, you're going to get 0 for y. So that's actually, so that's kind of confusing there, I know, but so those are intervals in part 1, but that's a coordinate, that's a point right here in part 2 of that answer. Concave up, nowhere, that's correct. That's kind of a weird way to phrase it, but that's all right. Concave down on 2 separate intervals. There, yep, both those intervals. And like I said, we have no inflection points. So D is definitely the correct answer to this problem. And number 44, an optimization problem, where we're going to cut square corners off the box, and we're trying to maximize the volume. So how much should we cut off to ensure that our folded box will have the largest possible volume? Now we have to pay attention to domain issues here. So we're letting X be the corner that amount we cut off, but there's only a maximum. Let's see, I wrote too large, but I'll talk about that. X can only be somewhere between 0 and 20, because if you actually cut 20 off each side, you've cut 40, which means you've cut the entire box. So technically, you could cut 19.5 or 19 point whatever inches off each side. It'd be a really silly looking box. It'd be so thin, but technically that would be valid in the realm of domain issues. So we have to remember any critical value that's 20 or larger we would throw out, and certainly a negative. So when you take x off each of these, your other two sides are going to be, that's left of the box, are going to be 40 minus 2x, 40 minus 2x. And then when you fold the flaps up, the height will be this x right here. So the volume is 40 minus 2x, 40 minus 2x times x. Sometimes I'll see students, they'll multiply this out and they'll forget to take the derivative before they try to solve this. But you got to remember, you have to take the derivative and set it equal to 0, not the original function. So now we have it as a function of x. So it's a little messy looking, but it's not that bad. It's pretty easy derivative. So you'll end up, when you multiply that, FOIL that out, 40 minus 2x, and then multiply it by x, you'll get this function right here. And then take the derivative, so you get 1600 minus 320x plus 12x squared. And I kind of rearranged the order of the terms for factoring purposes. So I factored a 4. That left 3x squared minus 80x plus 400. You could use quadratic formula if you wanted to, or you could even graph that function in the calculator and see where the x-intercepts are. That would work too. But we'll have it'll factor into 3x minus 20 and x minus 20. So the x minus 20 gives you a critical number of 20, which we already said earlier, that's too large. Greater than or equal to 20 is too much. So, but we are interested in this other one, 3x minus 20, which when you set that equal to 0, will give you 20 thirds. And so then that gives you the value for x, and to get the other dimensions, you plug the 20 thirds back into the 40 minus 2x. So 20 over 3 is 6.6667, there. So it's rounded to 6.7. And then when you plug 20 thirds in there, you get 80 over 3, which is 26.7. So the answer is A. Then the volume would be those three numbers multiplied together. 20 over 3 times 80. Yeah, there it is. 80 over 3, 80 over 3 times 20 over 3. That would be your volume.